Okay, guys, having taken a look at the exercises that I set you for this chapter, there's a few cases where I wanted you to fill in a few details, but it really is only covering material that we discussed in the lecture. So there really isn't anything that I feel that I really have to go through. I thought what would be useful, though, is to just recap the main ideas of this lecture. So, okay, so what was one of the key things that we wanted to show? Well, we were starting to study the path integral quantization of the field theory. And we said this particular quantity over here, the integral over the field of e to the is times the product of fields, is actually related to this quantity over here, which we calculated using operators. And this was the time-ordered correlation function calculated using Fock space and all of that apparatus of Fock space. And we said a nice way to get hold of the complete set of these integrals, so there's an infinite number of them, is to rather just evaluate one integral for z of j, and then we can get all of the integrals we want just by taking functional derivatives and evaluating the result at j is equal to 0. Z of j is often called the generating functional of correlation functions, or you could call it the generating functional of time-ordered correlation functions. Generating functional because it generates these correlation functions upon taking functional derivatives. Well, we were able to do this integral quite straightforwardly, actually by mimicking Gaussian integral in one dimension, and we got the answer that sits inside the blue box. So then, using the equality between the two green underlined quantities, we got what is sitting in the last red box on the page. So that we had a prediction that the time-ordered correlator of two fields should be related to the Green's function. And to get hold of the Green's function, we need to solve this differential equation in the green box. We did that by going to Fourier space. And the result is the last formula on this slide. And remember, this plus I epsilon prescription, this was equivalent to specifying some boundary conditions. And this is called Feynman's I epsilon prescription. So we explicitly did the integral over P naught by the residue theorem, and we got exactly the formula that we had obtained previously by operator methods. So I only showed it to you for the 2-point function, but you could go ahead for any n-point correlation function. The equality between the two green underlined quantities is perfect. It holds. And we've just been studying the free theory, but I'm telling the equality between the green underlined quantities holds even if you add interactions. And adding interactions is most easily done in the path integral, and deriving Feynman rules for interacting quantum field theories is most easily done in the path integral. That's true for scalar fields, but for theories with gauge symmetry, it's even more true. I mean, theories with gauge symmetry are quantized much more easily using the path integral. And that's why we have developed this path integral point of view. Good. Let's get cracking with the next chapter.